remember where we are. We are talking about inner product spaces, right? So you're taking an abstract vector space, and if you're lucky, you can put something on it that's like the dot product, right? You can put something called an inner product on it. Inner product is something that has properties similar to the dot product. And what we're saying is that we can basically do a lot of things that we do in Euclidean space in these inner product spaces. Okay, so we said that the next thing we're going to do was the Cauchy-Schwarz inequality. Cauchy-Schwarz inequality, right? And I don't know if you remember the Cauchy-Schwarz inequality, but you should. Can somebody tell me the Cauchy-Schwarz inequality? I have an entire book in my office called the Cauchy-Schwarz Inequality Masterclass. The whole book is about the Cauchy-Schwarz inequality, about different ways of looking at it, different ways of proving it, stuff like that. So, I mean, I wouldn't say it's like the most important thing in mathematics, but it's kind of important. It's not. It's far from the most important thing in mathematics. But what I mean to say is it's something interesting. Cauchy-Schwarz inequality, right, says that if you have if u and v are vectors in Rn, then the magnitude of u dot v is controlled by the magnitude of u times the magnitude of v. Okay, and why this is true, at least in 2 or 3 dimensions, it's easy to see geometrically. So in R2 or R3, we have this geometric interpretation of the dot product, right? That the dot product of 2 vectors is actually the product of the magnitudes times something. Times what?
The cosine of the angle.
Times the cosine of the angle between them, right? So you've got these 2 vectors, you've got some angle between them, right? The dot product actually has this meaning. Product of the magnitudes times the cosine of the angle between them, right? And so if you take the absolute value of that, well, the absolute value of the dot product equals the product of the magnitudes times the absolute value of the cosine. Right? But what do we know about the absolute value of the cosine? How big could the absolute value of the cosine be? At most, it's going to be 1, right? So this is less than or equal to, this is less than or equal to the product of the magnitudes. Okay. So in Euclidean space, at least in 2 or 3 dimensions, this statement is pretty clear. You just use the law of cosines to get the geometric interpretation, blah, blah, blah. Okay. But what if we're in an abstract vector space, right? You've got 2 functions, right? Do we have any sort of geometric interpretation of the dot product? Right? Is the inner product that we defined last time, is there some angle between the two functions? No, right? So you can't do anything like this. This does not work at all in the abstract case. Okay. So we have to go a different way. So let me just write it up formally. you suppose you've got U and V in an inner product space, then the absolute value of the inner product is less than or equal to the magnitudes, the product of the norms. Okay, and there's actually a second part. Further, equality holds if and only if U and V are linearly dependent. If and only if U and V are linearly dependent. Okay, so to get this, we're going to need two lemmas. We'll need two lemmas. We need two lemmas. Lemma one. Suppose that you have some non-zero vector v, and U and V are in your inner product space, and P is the projection of U onto V. Okay. Let me just say, I'll write both of them down here. So lemma number one says that U minus P is perpendicular to P. Lemma number two says U equals P if and only if U is beta V for some beta in R. Right? In other words, U is some multiple of V. Okay, so the pictures for these are, in Euclidean space, you have these pictures, right? You've got two vectors, U and V, right? You've got the projection P, right? You've got the projection P of U onto V. Okay? And what this is saying is that if you take U minus P, well, the thing that you get, this is U minus P in the picture, right? U minus P is going to be perpendicular to P. Okay? U minus P is perpendicular to P. Further, U would be equal to P if and only if U is actually lying on V already. Okay? But it's going to be equal to its if it's equal to its projection, that means that it actually lies on V, right? And vice versa. If it lies on V, then it's equal to its projection. Okay, so that's the picture. But of course, we're in abstract Euclideans. We are in an abstract inner product space, so there is no picture. Okay, so you have to remember there is no picture, right? This is the picture for Euclidean space. There is no picture for our inner product space. Okay, so this is some sort of like false picture, right? Because you don't know. It doesn't look like this. There's no picture, but there's no triangle or anything like that. Okay. So, but the thing is that still it's going to work. Okay. So let's do the proof. The first part, right? We want to see that U minus P is perpendicular to P. Okay. Well, this is just a calculation. Do a calculation. Well, right, to show these guys are perpendicular, we need to show that the inner product is 0, right? That's what perpendicular means. We need to show that the inner product is 0, so we do the calculation. We say, okay, u minus p, well, what's p? P is uv over v inner product v against times v, right? So this is u minus p, right? This is u minus p, and then we have p uv over vv v equals 0. Okay, so you need to show that you need to do the calculation here and show that you get 0. Okay. Maybe try it. Okay, take a minute. I was going to leave it as an exercise, but maybe I'll have you start it here. Okay. Try it. Just to check if you understand how to use the inner product. Right. So can you multiply? Okay, I don't want to use too much time on this, so let's do it. So let's do the calculation. So let's see. If we multiply these two things together, then we can use linearity, right? We can use linearity and say that this is the same thing as this is u against p, right? This is u against p minus p against p. Right? Okay. What else can we do using linearity? Say, well, we can pull this constant out, right? These things, don't get confused. These things are numbers, right? These guys are vectors. These are you're scaling the vector by some number, right? So you can pull those scalars out, right? So you get uv over vv, and you're left with uv here. Right, and then over here you can pull the scalar out. You pull another copy of the scalar out. Right, and you're left with vv. Right. Everybody okay? Anybody confused? Anybody confused? Anybody confused? So look, right? We've got u. We've got some multiple of v. We've got that same multiple of v. That same multiple of v. Right? let me call this scalar alpha, right? All I'm saying is that I can pull that alpha out. Right? I can pull that alpha out. Okay, but now we can cancel, and we see that we get 0. Right? You get this minus that, which is the same thing. Okay, so this is, maybe I shouldn't have spent time on this because it's just a calculation. Okay, so that's our first lemma. In an inner product space, U minus projection is perpendicular to the projection, just like it is in the normal Euclidean space. Any questions? Ellie, do you have a question? No? Okay. Proof of number two, right? That U equals, if U equals P, if U equals the projection, then U equals beta V for some beta in R. Okay. If and only if, right? So let's see the forwards direction, right? If U equals the projection, is U some multiple of V? If U equals the projection, this is just remembering the definition. What's the projection, right? The projection, remember, is UV over VV times V, right? So if U equals the projection, it's definitely a multiple of V, right? That's what the projection is. The projection is some number times V, right? So this direction is trivial, right? Trivial. Right. It's true by definition, right? True by definition of P. Okay. What about the backwards direction? If U is beta V, then U equals its own projection. Right? So if U equals beta V, then what's the projection, right? Then P, the projection is going to be U V over V V of V, right? What are we going to do? What do we do next? Nico?
Pull out the beta.
Pull out the beta, right? The beta. Did you say beta?
No, beta.
Okay. Actually, I think the pronunciation is beta.
Right.
Like the Greeks will. I'm pretty sure it's beta. Yeah. Pull out the beta. Yeah, this is America. We'll call it beta. Yeah, a friend of mine in Chicago once was teaching a class, and there were some Greek students in the class. And at one point, they came up to him and they said, "Could you not do so? In the class, you used alpha and you used a as different variables. Could you not do that? Because to us Greeks, those are the same letter. This is an A and that's an A." And he said to them, "This is America." Right. Which I'm afraid is the right answer, right? Because we do distinguish between alpha and A. Insensitive as that answer was. Okay. So yeah. So you see that then P and U are the same. Okay. Right. So if U is a multiple of V, then its projection is itself. Okay. So let me rewrite the theorem here. The theorem that we're going to prove, I'm just about to erase it. Right? So U and V are in an inner product space. So I'm just rewriting the Cauchy-Schwarz inequality. Then the inner product, the absolute value of the inner product is less than or equal to the product of the magnitudes, and equality holds. So, and equality holds if and only if U and V are linearly dependent. Okay, so proof starts off with something silly, which is that note if V equals 0, then we're done. Right, then the proof is trivial. Then the proof is easy. If V equals 0, right, then certainly the dot product, the absolute value of the inner product, is going to be less than or equal to the product of the magnitudes. We'd just be saying 0 is less than or equal to 0. That's certainly true. Okay, so we can assume that V is non-zero. Okay, so let's think. We want to show, it's always a good idea to keep in mind what you want to show. So like think, what are we trying to show? We're trying to show that this is less than or equal to this. And now we're going to rewrite the thing that we want to show, just in a minor way. That is the same thing as saying that this is less than or equal to this. Right? Okay. Actually, let me say something in the middle between that. Sorry. That's the same thing as seeing that the square of this is less than or equal to the square of this. Okay, and the reason for that is that because for positive numbers, A is bigger than B if and only if A squared is bigger than B squared. Okay, so to show that these are all positive numbers, so if I want to show that this guy is less than or equal to that, let me write this. If I need to show that this guy is less than or equal to that, it's the same thing as showing that this guy's square is less than or equal to that guy's square. Okay, and it's not true in general, but as long as they're positive, it's okay. So that justifies me changing this a little bit. Okay, and now I'm going to say, well, that's the same thing as UV squared over U squared is less than or equal to V squared is less than or equal to U squared. Okay, but what's this thing? Does anybody recognize this? Let me move the square to the outside. Does anybody recognize this? Excuse me. This is not the So this is the, Russ? Scalar projection, right? In other words, this is, well, I guess it has the absolute value on it. So it's the absolute value of the scalar projection, right? In other words, this is actually the norm squared of the projection, right? This is the norm of the projection squared, where P is the projection of U on V. Okay, so that's what we want to show, right? So we've changed what we want to show, or we've sort of changed our viewpoint of what we want to show, right? What we want to show is that the norm of the projection squared is less than or equal to the norm of the vector squared. Okay, but by the Pythagorean theorem, so we have, again, this the picture doesn't exist, but we're going to use it. Okay, so you have your U, you have your P, you have your P, you have your U minus P. Okay. Right. Again, there is no picture, but even so, we just showed that in our lemmas, remember, that U minus P and P were perpendicular, right? Recall, we just showed that U minus P was perpendicular to P, right? And so we can use the Pythagorean theorem, right? Pythagorean theorem says that norm of P squared plus norm of U minus P squared equals the norm of U squared. Right? Right? But what does that tell you? The norm of P squared plus something equals the norm of U squared, right? So the norm of P squared has to be less than or equal to the norm of U squared, right? Because it plus some positive number is that, right? So this has to be less than or equal to that. Oops, this has to be less than or equal to that, right? Okay, so we see that the norm of P squared is less than or equal to the norm of U squared, and in fact, and equality holds if and only if U equals P. U equals P. Right? The only way that this is going to be equal to that is if this is 0. Right? The only way this will be equal to that is if this guy is 0. Right? In other words, U and P would have to be the same thing. Right? So equality is going to hold if and only if U equals P. And that's the end of the proof. Right, if and only if U equals P. In other words, if and only if U is a multiple of P by the second lemma. So that's the proof of Cauchy-Schwarz, right? That the size of the magnitude of the inner product is controlled by the product of the magnitudes, and you have equality if and only if one guy is a multiple of the other. Okay, any questions? questions? Anybody confused? It's okay to be confused, actually. Okay, let's go on. Okay, so we do something funny at this point, which is we use this fact to make up angles between vectors in an abstract vector inner product space, right? There are no angles between functions, but we're going to make up something that acts like an angle. Okay, so given two vectors, u and v, in an inner product space, we define the angle between them to be the arc cosine of uv over the product of the magnitudes. We define the angle between them to be the arc cosine of the inner product over the product of the magnitudes. Right? Okay, we can do this. This makes sense because we know that the absolute value of this thing is less than or equal to 1. So this thing lies between -1 and 1 by the Cauchy-Schwarz inequality. So this makes sense. Right? We needed the Cauchy-Schwarz inequality to make this definition, because otherwise we don't know that the size of this is small, between -1 and 1. Right? We don't know that we can take the arc cosine of it. Now we do. Okay. So, right, so we define the angle, and then once we've defined the angle in that way, by construction, we have the geometric definition of the inner product, right? But that's nothing miraculous. We made up the angle so that happens. Okay. So the inner product also has a geometric interpretation because we made it have one, right? We define the angle so that happens. Okay. So that is the end of part of that section. Now we're going to start like the last topic in this section called norms. Norm, a norm is just something like a magnitude. Okay, so it's a generalized magnitude. So you remember when we had a vector and then we divided by its size? We call this thing like the normalized vector. Right? That's because we divided it by its norm. You have to watch out a little bit because there's another word, normal, in mathematics, which means perpendicular, like the normal vector. That's actually a different usage. Okay, so this normalized refers to norm, magnitude norm, but normal vector refers to perpendicularity, which is a different thing. Okay, so don't get confused. It's two uses of the word normal. Okay, so V, a vector space. So not necessarily an inner product space, just a vector space. If there exists a function going from B to R such that that the value of the function is always positive, and the value is 0 if and only if the vector is 0. 2, if you so let me say it this way. I'm sorry. Sorry. I know you're gonna start erasing. Sorry. So let blah 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 from B to R be a function. We call it a norm if the following 3 things hold. Okay. First, the norm of anything has to be bigger than or equal to 0, and the norm is 0 if and only if the vector is 0. Second, the norm of a scaling of a vector is the product of the absolute value of the vector, absolute value of the scalar times the norm of the vector. And 3, the norm of a sum of vectors is less than or equal to the sum of the norms of the vectors. Okay, this last thing is called the triangle inequality. If it satisfies these 3 properties. Okay. We call it a norm if it satisfies these properties. Which are things that the magnitude does, right? If you think about the magnitude of a vector, well, it satisfies all these properties, right? Our old Euclidean magnitude definitely does this. Okay. Further, in that case, we call V a normed vector space or normed linear space. Okay, so norm is basically just a way of finding a size, okay, talking about the size of a vector, right? But you want the size to have certain properties that, that your normal ideas of size satisfy. Okay, so here are a bunch of important examples of norms. So on Rn, so you have already one way of defining the magnitude, right? The magnitude of a vector on Rn, you take the sum of the squares of the entries to the 1/2 power, right? That's your normal Euclidean norm. But we can have actually multiple ways of defining norms. Okay, so here is one. For V in Rn, we define what's called the little L1 norm. Okay, this is called the little L1 norm. We define the little L1 norm as the sum of the absolute values of the entries. So, if I have some vector, V equals, say, -1, 1, then its little L1 norm is just the sum of the absolute values of the entries. Okay. Right? If you were a kid and somebody said, you know, how are we going to count how big this thing is? Well, this is maybe when you would do it. You say, well, I'm going to just take the magnitudes of each of these guys and add them together. Right? Take the magnitude and just add them together. Right? I've got my vector. Right? I'm going to take this length, and I'm going to take this length, and I'm going to add them together. And I'm going to call that I'll call that the magnitude of my vector. Right? So I take the magnitude of x, I take the magnitude of y, right? And that's my little L1 norm. Okay. Right. Now we are already familiar with what's actually called the little L2 norm, which is you take the sum of the absolute values squared to the 1/2 power. Okay. That's actually called the little L2 norm. Okay, and you can guess that there's nothing special about this 2. Well, actually, there's a lot special about the 2, but we can't get into that. But you could replace the 2 with some general number, p. Okay, and so this is the little LP norm for p bigger than 1. Bigger than or equal to 1. Okay. There's another norm called the little L infinity norm, where what you do is you take the maximum of the absolute values. You take the maximum of the absolute values of the entries. Okay. Now, we actually do have to show that all these things are norms. We're saying that we're calling these norms, but we haven't proven that they satisfy all 3 properties. Okay. Some of your homework will be to show that these things actually are norms, I think. Okay. Example 4. So actually, let me change this. It's not really example 4. So it's not on Rn. On an inner product space, suppose V has an inner product on it. On any inner product space, the function defined by taking the inner product of a vector against itself and then its square root turns out to be a norm. Once you have a norm, you can actually define distance. Okay, so you can talk about the distance between two functions or 2 vectors. Given a normed vector space, we can define the distance between 2 vectors as the norm of the difference. Okay. just like in Euclidean space, right? If you take the magnitude of the difference of two vectors, that gives you the distance between those two vectors. Okay, so you can talk about distance and stuff. Okay, let me end with something that's kind of fun. What's the unit ball? So the unit ball in R2. So if we think about our usual Euclidean norm, the L2 norm, well, the guys who are distance 0 from the origin, you know what they look like, right? The distance, if they're distance 1 from the origin, 1 or less, then it looks like this, right? This is the unit disk. So this is the unit disk with respect to the L2 norm, right? That's what the unit disk looks like. What about with respect to the L1 norm? What does the unit disk look like? It'll be everything of size 1 or less, right? So what kind of vectors have size 1 or less with a little L1 norm? Well, the sum of the magnitudes, the sum of the absolute values of the entries would have to be 1 or less, right? So somebody tell me some points that are in the L1 unit disk. Is, for example, so here's 1, negative 1, 1, negative 1. Right. Is this point in the unit disk? Sure, right? Because the sum of the magnitude, sum of the absolute values of its entries is less than 1. Right? All these guys are in, right? What about this guy over here? 1, 1. No, right? Do you see the shape of it? Does anybody see the shape of it? It's going to be... Yep.
It's going to be a circle.
Not a circle. Not a circle. Right? You want absolute value of x plus the absolute value of y to be less than or equal to 1, right? Right? So what's it going to look like? Well, see ya? It'll be a square. It'll be a square. Right? So that's the unit ball with respect to the L1 norm. Okay. What about with respect to the L infinity norm? What's that going to look like? Well, you need the max of x and y to be less than or equal to 1. What's that look like? As long as the entries are less than or equal to 1 in absolute value, you're good. So what's that? Is this point in? 1, 1, is that in? As long as the maximum of those entries is less than or equal to 1, you're good. So yeah, 1, 1 is in, right? These guys, these corner points are all in. In fact, you get another square on a different line. Right? So this is the unit ball, right? So you start off, L1 is here, L2 is like this, and as P gets bigger, it sort of fattens out. It fattens out to, right? So L1 starts off like this, L2 like this, right? And they get fat, sort of more and more irregular. Well, I don't know. They get more fat until they fill out the square. They get closer and closer to the square as P goes to infinity. There's some place in Europe where they use one of these paths as like in architecture, or maybe in street planning or something like that, just for the heck of it. Okay, that's it for today. See you next time.